All right, so our new unit is going to be talking about what are known as exponential functions. Now, we've actually done some exponentials before. We've done a lot with exponential equations and exponential laws. But now we're going to tie that into basically how they're going to graph and how they're going to generally look, as well as also going to tie into what are known as logarithms. Because in order to finally understand logarithms, we're actually going to have to know what exponentials are. Of course, there's the outcomes that relate to our exponentials. Exponentials and logarithms could technically be taught together, but it is a lot easier treating them as their own separate entities. But they are very closely related. So overall, we want to be able to understand exponential functions, including how they have their own horizontal asymptotes like we do in our rational functions, sketching them, and talking about transformations, as well as basically just kind of some general equation stuff. So the first thing that we're going to talk about is the characteristics of exponential functions. And the long story short is exponential functions are anything that go up or down by a separate portion. The graph of an exponential function, such as y equals c to the power of x. Now we're using c because we've talked about a's and b's being transformations, same with our h's and k's, but c is basically just a general base. C, actually, that's a nice little note. It's just the base. And it's going to be a number. Now, if the c is greater than 1, it's going to be increasing. And if the c is in between 0 and 1, that's going to be decreasing. Now, we'll talk about other transformations in another section. Well, generally, this is what it's going to be. If our c value, whatever this base is bigger than 1, like 2, 3, 17, it's going to be an increasing function. As it goes from left to right, it's going to be rising. Whereas when our c value is in between 0 and 1, it's going to be what's known as the decreasing function. So as reading from left to right, it starts up high and it keeps on going lower and lower. It is neither increasing nor is it decreasing whenever our base value is equal to 1. As a verb, generally, 1 to the power of anything is always going to be 1, which really just means that you have a horizontal line. From the graph, we can determine some characteristics like domain and range, any intercepts, and any asymptotes. So what we're going to do is we're going to use the table to determine some points, then identify the following. First off, we're going to talk about what the domain and ranges are, X-intercepts and Y-intercepts if they exist, and whether the graph represents an increasing or decreasing function, as well as the equation of the horizontal asymptote. That's a good thing that we've talked about what the horizontal asymptotes are with our rational functions. So let's get into it. Now, this is definitely something that I do need to put into my note package, is I like using the values -2, -1, 0, 1, and 2. Make that actually look like a 2. And I'm going to fill that in for both of these. Make that actually look like a 0, 1, and 2. All right. In the first one, our y is defined as 4 to the power of x. So 4 to the power of -2. Our x is -2. If we use our exponent laws back from grade 10, the negative means that we have to flip our base. We have 1/4, and our exponent of the 2 would just be turned positive. The negative just flips that base. Further on to that 2 gets distributed onto our numerator and onto our denominator, which makes it 1 squared and 4 squared. 1 squared is 1, 4 squared is 16. So 1/16, very small number. Of course, not the smallest number that we've ever dealt with, but it is still a small number. Similarly, -1. 4 to the power of -1. Just the same. The negative just flips our base to be 1/4. Now it would be raised to the power of 1, and we distribute that 1 exponent onto the numerator and to the denominator. But it really doesn't change anything because 1 to the power of 1 is 1, and 4 to the power of 1 is 4. Then we go into the fancier side, 4 to the power of 0. 0 being our x. Of course, like we remember back from grade 9, anything to the power of 0 will always just be 1. So that one's nice and easy. 4, don't have to do any extra work for 1 and 2 because 4 to the power of 1 is 4, and 4 to the power of 2 is 16. But let's just do a quick little sketch of what this would actually look like. Doesn't have to be anything too fancy. Down at -2, we're at 1/16, which would just be a little bit above the x-axis. At -1, it'd be 1/4, which obviously is a little bit bigger. It's 0.25. At 0, the equation would be up at 1, or our graph would be up at 1. At 1, we'd be up at 4. Now, trying to make this as proportional as possible. Of course, by the time that we get 2, we're up at 16, which is already off our entire sketch. So all we have to really worry about is connecting these dots. And knowing that that graph goes really high. Which leads us into what our entire question is talking about. Domain, range, x-intercept, y-intercept, if they exist, whether it represents an increasing or decreasing function, and the equation of the horizontal asymptote. So let's talk about the domain and range first. Our domain, as this is something that extends to the left and extends as it keeps on going to the right, it does keep on going up, but it does keep on going to the right. It is all of our real numbers. You can plug any value in for x, and it's going to produce a number. Of course, the smaller the number, so -15 umptillion, is going to make the y extremely small. That would never equal 0. Similarly, if you put anything in for x that's super big, like 17 octillion, well, that would make this extremely big. It would just keep on rising. Which leads directly into what our range would be. Because as our y's keep on going down, this graph does keep on getting closer and closer and closer and closer to that x-axis. But no matter what you do, it's never going to cross. It's never going to hit that x-axis. Which means that our range is just our y's that are greater than 0. That's an element of the real numbers because it could still be all the real numbers, but just ones that are greater than 0. Then we talk about the x-intercept. Well, similarly to our range, if it's never going to hit our x-axis, we're not going to have any x-intercept. So we can just simply say that there is no x-intercept. And as you go through with a line through it, NA, not available, not applicable. But we do have a y-intercept here. Where is it crossing our y-axis? Well, it's crossing our y-axis when x equals 0, which means our y-intercept is 1. Is this an increasing or decreasing function? Well, you can see from this graph, as well as from the equation, and I'll talk about that in just a second, that this is definitely an increasing function. And I'm just going to use the abbreviation of I and C. The reason I say that, we can look from the equation for the 4 to the power of x, the base value of 4 is definitely bigger than 1. And any increasing function is going to have a c value greater than 1, provided that we don't have any extra transformations in here, which, yes, we will talk about, but we're not going to be doing that in this section. Because generally, we're just going to talk about the base. We're just learning what the exponentials are here. And since that 4 is definitely bigger than 1, it's an increasing function. Now, moving on to everyone's favorite asymptote that you can actually cross, but very similarly do, which tie directly into our limits, which some of you will be doing in calculus, or horizontal asymptote, something that generally is never crossed. Well, in this case, it's our x-axis. So the equation of that horizontal asymptote is y equals 0. All right, let's go into the more fun stuff. 1/2 to the power of x. So 1/2 to the power of -2. Well, a negative exponent means we flip the base, so instead of 1/2, it's 2. The exponent just turns positive. 2 squared is 4. If we do the -1, 1/2 to the power of -1, well, that 1/2 just flips our base. It's 2. The exponent just turns positive. 2 to the power of 1. And this one's 2. We know that 1/2 to the power of 0 is just going to be 1. Anything to the power of 0 is 1. 1/2 to the power of 1. So if that was a 1, we'd be distributing that 1 onto the numerator and onto the denominator, making it 1/2. If that x instead was 2, same thing. We distribute onto numerator and onto the denominator. 1 squared is 1. 2 squared is 4. I'm going to erase that off. If we do a nice little sketch of this, because it doesn't hurt to have a little sketch, of course, you can say in A, you will have Desmos, so use it. At -2, our graph is going to be up at 4. At an x value of -1, our value is going to be at 2. I'm just trying to make it as proportional as possible, just to make it nice and graphable. At 0, we're at 1. At 1, we're at 1/2. At 2, we're at 1/4. So you can see that as we can connect these dots, this is how it generally tends. Now, I'll make a note about how you can see basically how fast things rise in just a second. But let's talk about those 6 things that we have up here: domain and range, x-intercept, y-intercept, graph representing increasing and decreasing, and the horizontal asymptote. Just like before, our domain is all of our x's that are an element of the real numbers. Our range, in this case y's, just like before, because even though this graph keeps on getting closer and closer and closer to the x-axis, it will never cross. So we y that are element of the real number, or y that are greater than 0, y is an element of the real numbers. If our range means that we're always going to be greater than 0, we have no x-intercept. Our y-intercept. For any function, our y-intercept always happens when x equals 0, which in this one is right there. It's y equals 1. The biggest difference on this one is, oh, this is definitely going down as it's going from left to right, which is evident in our equation and obviously from the graph. 1/2 is definitely in between 0 and 1. It's in between 0 and 1, which makes it a decreasing function. And a nice abbreviation of that, DEC. And once again, just like before, our horizontal asymptote is y equals 0. I just want to make a quick note about how you can see that this 4 to the power of x definitely seems to be rising a lot faster than this 1/2 to the power of x is falling. And the general rule for that is the closer value, or the closer that the base is to the number 1, the basically less steep it's going to be. Since 4 is actually much further away than 1/2 is from 1, it rises at a much greater rate. So how can you really tell? I guess, yes, C could technically go to 1,000, but you can't get really 1,000 away from 1 here. It just comes down to that same proportion. Again, proportions. Proportionately, 4 is 4 times as big as 1. 1/2 is actually only half the size. Or in other words, 1 is twice the size as 1/2. So 4 times as big for this one, or the number 1 is twice as big as this one. Well, it's going to be a lot more less steep because 1/2 is way kind of closer to the number 1. That's just kind of a little fun tidbit because math is always fun. Now, if we want to talk about basically determining an equation, we want to take a general look at what our numbers are. So in this case, just so you are fully aware, this point is useless, the point 0, 1. Because it doesn't matter what you plug in for C, as long as if this is just the base form with no transformations, the point 0, 1 is never going to change. Because I could plug any number in. Well, as long as it's a number, not 0. And it's going to be a number to the power of 0 will always equal 1. So this is a bad point. So what we want to do is look at the other points. What number? So again, this is a bad point. We need to find a number that when raised to the power of -1, it's going to equal 4. Because that's what that point is telling us. Some number raised to the power of 1 is going to give us 4. The exact same number when raised to the power of -2 is going to have to give us 16. Now let's look at some other characteristics. We know that this is definitely a decreasing function. Make that actually look like a C. Since it's a decreasing function, we know that our C value has to be between 0 and 1. I mean, we can't choose the number 0, or can't choose the number 2. We can't choose the number 3. We can't use anything that's bigger than 1. It has to be somewhere between 0 and 1. And this 1 is actually a really fantastic way of treating it. So we need to know what number, when you literally just take the inverse of it, is going to give us 4. What number, when you flip it, it gives us 4? 1/4 is the only number that works. As you take that negative, you flip your base, 4 to the power of 1 is still 4. If you do the exact same thing with the -2, 1/4 to the power of that -2, you flip the base. Let's kind of do a little side note here. You flip that base because of that negative, now that's becoming 4 to the power of 2. 4 to the power of 2 is 16. So determining the equation, sometimes it takes a little bit of extra work. It takes a little bit of some good educated guessing. Now, just for the science bit, talking about some biology, some ecosystems, talking about even radiology, which is actually example 3, which is I love introducing it as part of as a physics standpoint, because radioactivity is really kind of interesting. Basically, if you have an A base and your C is greater than 1, it's called exponential growth, which can be kind of modeled with, for example, the human population increasing at a very unstable exponential proportionate way. Or we could talk about exponential decay, which kind of talks about how things break down, and that is exactly what radioactivity does. Because radioactivity does have a decay, or in many times it talks about what's known as a half-life, which is used a lot of times for carbon dating or for determining kind of how long things can remain dangerous. Scientists will use carbon dating, which basically tells how long the carbon was, or how much carbon is left within certain organisms for being able to date certain genetic samples. For example, bones, saying that, oh yeah, these mammoths or whatever are 38,000 years old, or this specific mastodon, or sorry, not mastodon, we're done with that. Some kind of dinosaur is 250 million years old. So that carbon dating measures the amount of carbon left within a certain sample. Whereas when we talk about the radioactivity, talk about that physics side, we talk about generally very dangerous chemicals, or not chemical, elements like radium or uranium, plutonium, everything like that. But radium is the one that we're going to talk about today. So the example is saying that a radioactive sample of radium-225, has a half-life of 15 days. Now what half-life of 15 days mean is that every 15 days, it's going to decay to only be 1/2 of its original mass, or just at 1/2 of its mass. So mass m in grams of radium-225 remaining over time, t in 15 intervals, can be modeled using an exponential graph shown. So obviously you can tell that this is also a decreasing graph, because decay has to be decreasing. And every single 15 days, every 15-day interval, so 1 15-day intervals, it has decayed to be 1/2 of its original size. Another 15 days, it has decayed to 1/2 of that size. So you can see that this is at 0.25. Another 15 days, which is three sessions, the 0.125 is 1/2 of that 0.25. Now, not every single radioactive element has a 15-day. For example, if you go into your elements that are much higher on the scale, which scientists are actually very close to being able to start into another row, but like element 118, the half-life is a fraction of a second. It takes is so small, it's impossible to actually read without proper scientific elements or instruments. But science. Okay, anyways, the initial mass of radium-220. What is the initial mass? So we just look at when was time 0. All right, that's easy. 1 gram. Can't read that. Well, what value does the mass of radium-225 remaining approach as time progresses, or as time passes? So as the time keeps on passing, what does it generally get closer to? Well, you can see it gets closer to 0 grams. Now it's going to be absolutely impossible to measure exactly that, because it's going to keep on going half and half and half and half. But for practical purposes, yes, it does get to pretty much 0. Just the same as when we talked about our arithmetic series and our geometric series last year in Pre-Calc 20, how if you go half the way every single time, yes, you'll get dangerously close. But for many practical applications, for example, if I go halfway across the room and halfway, half, I can eventually get closer and closer to the filing cabinets. And throughout time, yeah, I'm going to definitely be close enough that I can use the filing cabinets for whatever I need to use it for. Okay, domain and range of this. So our domain, what is relevant? on this one, so our x's are greater than or equal to 0. Yeah, we can't have negative values on here because we're not talking about negative time. For our range, we have to talk about what is the lowest value that our range is going to get. Well, it's going to get dangerously close to 0, but it's never going to actually equal 0. So 0 is less than or equal to, or sorry, less than y, less than or equal to, so I'm going to have to actually erase that because that looks really bad. Less than or equal to, and the highest value it's going to get is 1. Because you can't, we're not talking about a sample that infinitely replaces itself. And there's our range. So C asks, what is the write the exponential decay model that relates to mass of radium-225 remaining in time in 15-day intervals? Well, this is actually a lot easier than possibly thinking. It's basically asking, what is the equation? What is the equation? So it's always going to be y equals. Long story short, we need to find out what is the base. It's actually really simple. It's what proportion is it going down by? It's going down by half. Every single time it's going down by a half. 1/2 to the power of x. Or you write t. Because we're talking about time. Same time we can talk about the mass being 1/2 to the power of t. So make that actually look nice. As best as I can. So I'm just going to erase this t and let my notes. Now the question to estimate how many days it would take for radium-225 to decay to 1/30th of its original mass. So we need to find out where does 1/30th happen. Now, there's two different ways we can deal with it. One way we can deal with it is basically finding out where does 1/30th appear on this, actually on this graph. If you type 1/30th into your calculator, which is just simply 1 divided by 30, you get 0.03 repeated. Well, that's not on here. It's definitely smaller than 0.125. So we need to keep on going. But there is actually a faster way because we're just kind of doing an estimate. 1/30 is really close to another number, which would actually be 1/2 to the power of something. So just for say, you don't have to write this part down, but 1/2 to the power of 1. So you can write the 1/2, but don't write the 1. We know to the power of 1 would be 1/2. If we wrote to the power of 2, it'd be 1/4. If we keep on going, we know that 3 would be 1/8. So I'll just show that. 1/2 to the power of 3 would be 1/8. 1/2 to the power of 4 makes it 1/16. Oh, sorry, power of 4 makes it 1/16. If we go one more step, whereas we make it to 1/2 to the power of 5, it would be 1/32. And 1/32 is going to be as close as we can get to the 1/30th. Now, obviously, this is actually a smaller number than 1/30th, so it would be a little bit before that 5 intervals. But then we have to look at it and say, oh, this is actually, this 5 is t, which is talking about 15-day intervals. So 5 15-day intervals actually comes out as what? 75? So 75 days. Obviously, it'd be a little bit before, possibly like day 73, 74, but this is an estimate. All right, that allows you to have some fun.